magnetic field of a coil. This is a coil. We look at the current is around one. Suppose around one. Current go in, and in this we cut half. This is out. Okay. But we want to find the magnetic field at point P, which is on its axis, central axis, a distance z from the coil. Now, we look at this IDS. Okay, the current is towards us. Okay, now this is a P, so this is R. The IB equal to IDS cross R. This IDS, this cross, so cross, you get this one, dB, perpendicular this and perpendicular this. Okay. Mu 0 4 pi IDS sine 90 degree pi sine, because this IDS is are perpendicular with each other. Now, if we take another IDS on the other side of the diameter of this ring, in this case the current go in, so we call it, this is IDS cross R. We get dB in this direction. By symmetry reason, we can know that the perpendicular to the axis, the component perpendicular to B bar, the equal and in opposite direction, they cancel out. Only the component along the z direction put together. Okay. So by symmetry reason, B is along a z axis. Okay. So how big? This is B. Okay. Equal to B parallel, all together around the coil. Okay. And B is D parallel is dB cosine alpha. This is cosine alpha. dB cosine alpha. And this alpha equal to this alpha. You see, this line parallel perpendicular this line perpendicular this line. So this alpha equal to this alpha. And from this triangle, cosine alpha is big R over small r. Okay? And the small r equal to z squared plus r squared square root. That's it, and we do it. B is altogether sigma integration B parallel to the z-axis, equal to dB cosine alpha. And cosine alpha equal to big R over square root R squared plus Z squared. And dB equal to mu 0 4 pi IDS sine 90 degree of R. Now, we do the calculation. It's very easy. Sine 90 degrees is 1. Okay. And the integration ds. And all these terms, nothing to do with s. So we take everything out of this integration. We get integration ds. This is for a coil, a round trip. So integration ds equal to 2 pi r. The circumference of the circle, the round. Okay? And we put this one is equal to m0I r squared. 2 pi, 4 pi can be 2. R squared plus z squared, 3 over 2. In the case, if z is much, much larger than r, then we drop this one. Z squared, 3 over 2 become z cubic. So B equal to mu 0 I r squared z. And we rewrite it. We put pi up and down. And pi r squared is the area of the coil. And so this IA. IA is the magnetic dipole of this coil with current I. Right? So this is the B. This B is the magnetic field on the axis by a current coil equal to this one, when Z is much larger than R. Let's look at it. The electric field produced by electric dipole. Remember that? We have 2 pi epsilon p over g squared compared to this one. This epsilon is in denominator and the mu 0 in the numerator. Okay, this is a magnetic dipole mu. This is an electric dipole p. This is very similar.
This animation shows a single loop of wire carrying a current in the direction shown by the arrows. We'll use the law of Biot-Savart to determine the direction of the resulting magnetic field along the axis of the loop. To find the magnetic field at point A, we first divide the wire into small sections, each carrying the same current. Each section of current contributes a magnetic field at A, which is at right angles to both the current and to the vector drawn from that section to point A, and whose magnitude is proportional to the current in that section. The total magnetic field at point A is equal to the sum of the magnetic fields created by all the sections of current. The magnetic field contribution from each of the current sections has a component at right angles to the axis of the loop and a component parallel to the axis. Since each current section has a corresponding current section on the opposite side of the loop, and since their components at right angles to the axis are equal and opposite, they cancel out. The components of their magnetic fields parallel to the axis add together, producing a net magnetic field along the axis of the loop. The magnitude of the field is proportional to the magnitude of the current in the coil, and inversely proportional to the square of the distance from the center of the loop.